So last time we calculated the matrix elements of silicon at K equal to 0, the gamma point, and we showed that at K, and well, the same thing would happen to gallium arsenide or any of these 3,5 zinc blende or diamond crystals. So at the K point, things became really simple. A lot of the matrix elements disappeared because of these 4 phase factors that show up. So wherever you had 4 phase factors, and like this, where 2 of them had a positive sign in front of them, 2 had a negative sign in front of them, K equals 0, they all disappear, and actually most of your matrix elements disappear. Finally, this whole 8 by 8 matrix at K equal to 0 became this. And so you only have matrix elements between these are off-diagonal matrix elements between a px state on the A atom and a px state on the B atom, and then a py state on the A atom and a py state on the B atom. So x couples to x, y couples to y, z couples to z, and there's no other coupling between the atoms. And so this whole problem reduces at K equal to 0 to the 2 by 2 matrix that you solved in homework 1. This is your homework 1 problem. Right? At K equals 0, this becomes your problem you did in homework 1. You had a 2 by 2 matrix, you brought 2 hydrogen atoms together, and you calculated what happened to the states. And you calculated the energies, you calculated the eigenstates. You calculated them both for if the site energies were the same, in which you had this covalent type bond where the probability on either atom is a half, and you had either symmetric combination or anti-symmetric combination. Or you calculated numerically the wave function for assuming the 2 site energies were different, like gallium arsenide, and you saw that the lower state was more heavily weighted on the lower energy orbital, and the antibonding, the higher energy state, was more heavily weighted on the higher energy orbital, as you would sort of intuitively expect. I mean, as you bring those atoms, if you move those atoms apart, the higher energy state is entirely on the upper energy, and the lower energy state's entirely on the lower energy. At any rate, we reduce this. This reduces to your homework 1 problem, which you know everything about. And we showed what happens for 2 specific cases in terms of how what happens to the energy splitting. At K equals 0, these sort of energy diagrams that you see in textbooks, where you have your levels before you bring the atoms together, and because of the bonding between the atoms, the energy levels split. Just like in homework 1, this is like that first concept that you did in homework 1 gets really applied over and over again. And just depending on how much their alignment to begin with and how much they split is going to depend on whether you have something that looks like you're a direct band gap material or not. For silicon, it's not. The S anti-bonding state ends up way up here. And so the conduction band at gamma is your P antibonding state. For germanium, that's not the case. You have, this is the configuration, this is a sort of splitting you see in the 3,5s in the direct gap materials, where your valence band is the P bonding states, your conduction band is your S antibonding state, and this is what you see in all the direct gap 3,5s like gallium arsenide. And if we write down what these states are, just to make sure that we know exactly what we're talking about. I don't think I wrote this down last time. But like these guys, it would be 1 over root 2 times, we need the bonding configuration, but since they're p orbitals, it's just a little funny. So you have an x, say, on the A atom minus the x on the B atom. right? There's going to be three states. The minus sign is there because, well, the orbitals are antisymmetric, so the antisymmetric combination of the antisymmetric orbitals gives you a symmetric state. This is what we talked about when we talked about, drew all those little pictures of the bonding and anti-bonding states. And you'd have three of them, and, well, the other two are just due to the y and z. And the third one is for the z. So just like in what you did in homework 1. Those would be the three bonding states that make up the valence band at gamma. And your S antibonding state is, there would only be one of them, so that's your 1 over root 2 SA minus SB. That's your S antibond. And then your P antibonding would be the I'd add these states together instead of subtracting them for the P antibonding up here. So it's exactly the kind of wave functions orbitals that you had in homework 1. So that's all there is to this would be for silicon or germanium where the two atoms are the same, and then in homework 1 you did two atoms that were different, and then you had the weight was more heavily on, say, whichever one the anion is, the lower energy one. If it were gallium arsenide, this would be weighted. Say gallium arsenide and arsenic was, I don't know, the A atom. Then you'd have a heavier weight on the A atom than on the B atom. And that would be the only difference. So that's the state of what the valence band looks like in the absence of spin-orbit coupling. And this is, for any of the direct gap semiconductors, this is what the conduction band is. It'll be a pure S state. It may, if the atoms are different, it'll be more heavily weighted on the cation. And this state is not going to be affected by spin-orbit coupling. So this is what it's always going to look like for a direct gap semiconductor, a pure linear combination of the s orbitals. And remember, this is a gamma state, k is 0, so this state is just, there's no phase factor. That phase factor is at 1. So that state is just repeated in every unit cell. Then we move down to spin-orbit coupling. And this is going to affect the valence band. It's going to, right now our valence band is threefold degenerate. Right? There's three orbitals here. They're all degenerate, and each one has two spins. And the spin-orbit coupling is going to break that degeneracy. This is the form of our spin-orbit coupling Hamiltonian, this L dot S. Proportional to L dot S with some strength. We'll see how that strength is related to the physical splitting of the valence bands. And so our total Hamiltonian is the sum of what we've done already, what I call H-type binding. This is what we've done already, the type binding Hamiltonian, and then this extra term that we're going to add. Hopefully finish adding today. This is the physical simple physics behind the spin-orbit coupling. The orbital angular momentum generates its magnetic field, which in turn interacts with the spin. The spin wants to be aligned or anti-aligned with the magnetic field, and there's an energy splitting depending on whether it's aligned or anti-aligned. And so the first thing is to just take our original basis, and for every orbital add a spin, an upspin and a downspin, which doubles the size of our basis. So for every orbital we have two spins. If we didn't have the spin-orbit coupling term and we just added, doubled our basis and looked at, what happens to the Hamiltonian, it's pretty trivial. You have the Hamiltonian we just wrote down in terms of, the A atom and the B atom, and I'll write it very sort of schematically. So this would be your, say, this is, what have we got? The A atom, in the B atom, and you've got your diagonal terms here, your diagonal terms of, you know, your on-site energies, and you've got your coupling matrices that couple the A atom to the B atom, and I'll call all of these my upspins, and then I would just double it, repeat everything, have again an A atom and the B atom. These would be my same set of basis orbitals, and these would all be downspin, and I'd have the exact same matrix in this lower corner that we just derived with the diagonal elements, diagonal, and my coupling matrices that are functions of K. So each one of these blocks I've drawn is 8 by 8. It's the same thing we wrote down before. We just doubled the size, and there would be absolutely nothing coupling these two big blocks. So this is if in the absence of, without this extra term that we're going to add. So this is sort of where we are. We've never bothered to explicitly include spin because it's kind of trivial. It just the Hamiltonians for both spins without the spin over coupling are absolutely the same. So you don't really need to write it down. But this is really what we've been doing all along. You've got this spin degeneracy that for each level we put at the end of the day we just put in an upspin and a downspin. And this explicitly shows our starting point, what things look like when you include spin in your basis, and why it's until you have this extra term here, it's kind of pointless to explicitly include it in your basis because everything's identical for the upspin and the downspin. But once we include this, we're going to get matrix elements in these blocks that couple these two, the upspin and the downspin world. And that's going to change things, at least in the valence band. For the P states, it's going to change things. And so then we started, what we need to do is we wrote down our Hamiltonian L dot S, lambda L dot S. And as always, we need to be able to take the matrix elements of the Hamiltonian. And so now what we're going to do is spend the rest of the afternoon figuring out how to take the matrix elements of L dot S. And the way we do it is make use of this identity, write the total angular momentum like this, and then just rearrange that second line to get L dot S in terms of J squared minus L squared minus S squared. And so this is the thing that we're really going to be taking the matrix elements of. This is what we're going to figure out how to take the matrix elements of. J squared minus L squared minus S squared. And that's going to do that. We're going to do a change of basis from the basis we've been using into what's called a total angular momentum basis. So first let's talk about a total angular momentum basis. Okay, and this basis we're going to write as in the same way we write just any angular momentum basis. So the total angular momentum is J, or maybe I can, what's the best way to, so J, maybe this is the way to say it, J squared, the operator J squared, acting on my total angular momentum state, is equal to what's it equal to? I guess this doesn't really define it well either. Well, let me just finish this sentence and we can go back. So it's h bar squared over 2 times the total angular momentum times J plus 1. In the same way, I don't know if you remember from Korotkov's course, that L squared acting on a total angular momentum state Lm. So these are YLMs. So this represents our YLM, which are what form our p states, our total angular momentum states. That's also equal to h bar squared over 2 times L plus 1. So in where L is your orbital angular momentum in this case, and m is the z component. I'll write m sub L since it's going to be multiple like m's. This is m. So over here, this is your total angular momentum, and this is the z component of your total angular momentum. Exactly analogous to your orbital angular momentum. These states, mj, which we're going to be using, so for these states, they're going to be simultaneous eigenstates of j squared, L squared, and S squared, where j is your total angular momentum, L is your orbital angular momentum, and S, maybe I should write S differently. Well, that's S. S is your spin angular momentum. So S is 1/2, always, right? The z component of S will be plus or minus 1/2, but S is 1/2 because we're just talking about a spin 1/2 electron. Right? S is 1/2, and the m component is plus or minus 1/2. For the p states, which are the ones we're interested in, because for the s states L is 0. For the p states L is 1, and so m sub L is 1, 0, or -1. Right? Because m can go from like -L to L. M can go from, the z component can go from -L to L. Well, the same thing, J, it turns out the possibilities for J are, turns out they can be 3/2 or 1/2. And depending on what J is, then you can have M going from -J to J. But given that these are simultaneous eigenstates of this, and we want to, and we're going to spend some time discussing how to go from our present basis into this basis. But given that you have this basis, and the reason, sort of motivation why we want this to work in this basis is that if you look at in this basis, if you go ahead and take the matrix elements of our L dot S, well, that's equal to h bar squared over 2 times j plus 1 minus L times L plus 1 minus S times S plus 1. And since these are eigenstates, simultaneous eigenstates of J, L, and S, and they just give you Kronecker delta as delta J prime delta MJ prime. In other words, in this basis, all these operators are diagonal in this basis. And that's why we want to work in this basis. So in this total angular momentum basis, all these operators are diagonal. We call these pure angular momentum states, and they're eigenfunctions of J squared. The basis that we're starting from, like S, what you call a direct product basis, or X down, for example, etc. These are what you call mixed states, and they're not eigenfunctions of J squared. Okay, so what we need to do is write these mixed states as a linear combination of the pure states, which is simply a change of basis. Okay, so we need to do a change of basis. I guess I have a few more words about the individual states before we do the change of basis. So these YLM, and these are, we are PX, PY, and PZ were just a linear combination of the YLM for L equal 1. They are pure angular momentum state, and so L squared YLM is. And if you have a pure angular momentum state and nothing else, if you don't have spin, then the total angular momentum is the orbital angular momentum, because that's the only angular momentum there is. The other thing we're starting from are spin. So we have up or down. And these guys are pure spin angular momentum. S squared hitting the upspin just gives you, I guess we need an h bar squared out front, h bar squared times s plus 1. So this spin s up or down is an eigenstate of s squared. For spin, s is 1/2, and if again this is all you have, just spin, then the total angular momentum is the spin angular momentum, and so j squared is s squared if all you have is spin hanging around. And also if you take sz, the operator that acts on the z component, that just gives you 1/2 h bar up. So these are also eigenstates of the z component of the z component of the momentum. And it would just be negative 1/2. And a similar thing would be for the YLMs. They're also eigenstates of LZ in the same way. So going back to our change of basis, getting ready for our change of basis. So individually, these states, the orbital angular momentum or the spin angular momentum, they're pure angular momentum states. So individually. And so we're going to write them using the notation of pure angular momentum as like this. This is sort of defining notation that we're going to use. So YLM we're going to write as an angular momentum state of J1 M1, where J1 is L and M1 is M. The L and the M of your YLM. Similarly, we're going to write our upspin as J2 M2, well, both are upspin and downspin, and using the same notation, J2 M2, where J2 is S, which is 1/2, and M2 is your plus or minus 1/2. M2 is SZ, which is your plus or minus 1/2. So we're going to be using this notation that we use for the total angular momentum states for each one. J1 will be for the orbital. J1 M1 represents the orbital angular momentum and Z component. J2 M2 is the spin angular momentum, spin angular momentum and Z component. And so our direct product states, which is our starting point, are YLM up and YLM down, right? So all our states we can represent like that. They're just direct products of the orbital and the spin angular momentum. And in this new notation, this is just a change of notation to get ready for the next step. We write that as J1 M1 J2 M2 So that's our direct product state. That's just the a change of notation at this point, but it's just a one-to-one correspondence. So J1 is L, J2 is S, M1 is the Z component of L, -1, 0, or 1. M2 is plus or minus a half. All right, so that's our direct product state that we're starting with, and we have to transform this into this total angular momentum state to calculate that matrix element of J squared minus L squared minus S squared. Okay, the total angular momentum state is J comma M, where J is equal to J1 plus or minus J2, which is 1 plus or minus a half, which gives possible values for J of 3/2 or 1/2. Okay, those are the possible values for the total angular momentum. And then you have the 2J plus 1 M values. So M can equal, well, it depends what J is. So M can equal for J equals 3/2, -3/2, -1/2, a half, or 3/2, or it can equal, if J is a half, it can equal -1/2 or a half. J equals 1/2, and is it J equals 3/2? We now need to transform from the direct product basis, which is what we've been using so far, into this new basis. And this goes back to the very first lecture of some basis transformation. We have this J1 M1, J2 M2, and we want to write this as a linear combination of the JMs. And so that's equal to a sum over J comma M of J comma M, J comma M. Notice, going back to one of our first lectures, that would be the identity operator, right? That's just an identity operator. And then hitting the state you run it. So the state occurs on both sides. J1, M1, J2, M2. So that's the way you'd write any basis transformation. And so now the whole question is, what the heck are these matrix elements? Because these will give you the weight, right? That Jm on the right side is the basis you want. That direct product on the left side is where you're starting from. These would be like your weights, your C, J comma M, right? These matrix elements are the weights that you're after. So you need to know how to evaluate that matrix element between these two base sets of basis states. And these things, fortunately, are tabulated in many places. They're very famous. They are known. So these matrix elements, your J1, M1, J2, M2, Jm, are the Clebsch-Gordon coefficients. They're real numbers. And so they're also equal to Jm, J1, M1, J2, M2. All right, they're tabulated, they're real numbers, and so it doesn't matter which way you write that matrix element. And I'm going to write down the table that shows how to go from one basis to the other. But before I do that, I understand this is all very mysterious. And when you derive this in physics, sort of second or third quarter physics, quantum mechanics, you spend about a week or so doing this. If you want to see more discussion somewhere. I think the cleanest discussion is in Schiff, which is one of the books listed in the syllabus. Everything he presents in his book is very sort of concise. I find it very clean, but maybe if you've never seen it before, it's a little too concise and too clean, and you want a little more description. Another place you can find it is in the textbook Alex, that out-of-print textbook that Alex uses in his course 202, EE 202. It also has an MSc number, which I can't remember. And so that's Sing. I don't know if you guys just get like photocopied pieces of it or what. But in Sing, you'll also find a discussion of this, pages 140 through 144. And also in Appendix D. Those are the two places where if you want to look more at this, and again, Sing goes through this discussion of spin orbit coupling. And Sing also, shows the same type of 8x8 Hamiltonian that we've already derived. It's a pretty good book. It's been a while since I've looked at it. My recollection was that, there are typos. You have to be careful. But, the description was pretty good in Sing. Okay, so the Clebsch-Gordon coefficients. So now I guess the thing to do is, let me just write down the table, this table of coefficients, which you need to go from one basis to the other. So this is going to be, what do we need? 1, 2, 3, 4, 6. So it's going to be a 6 by 6 matrix. Down here I'm going to have the M1, M2 of my direct product basis and -1, -1/2. So the left column is L, right? And the right column is, or LZ, the Z component of L, going from -1, 0, and 1. And the column to the right is did I leave off on -1/2 here? The Z component of S, the spin, right? It's either 1/2 or -1/2. So this is our direct product state here. I didn't leave enough room to write it in the right orientation. J1, M1, J2, M2. So I'm writing our direct product state there, and then on this going across the top, I'll have our total angular momentum state, Jm, and so this is going to be 3/2, 3/2. So this is the total angular momentum and the z component, J and M, is what I'm writing across the top. 3/2, 1/2, then 1/2, 1/2, 3/2. I don't know why they order it like this. I think to make the table look, you'll see when we finish the table out. 3/2, -1/2, 1/2, -1/2, and 3/2, -3/2. Okay, and so up top, I'm writing our Jm states, our total angular momentum states. Okay, now we just need to fill in the matrix element. So the matrix element between the direct product state with M1 is 1 and M2 is 1/2, with the 3/2, 3/2 state is just 1. And that's the only matrix element in that row. So there's a one-to-one correspondence. I mean, the direct product state with L equal 1 and, I'm sorry, with LZ equal to 1 and M, how do I say this? The Z component of L is 1, the Z component of S is 1/2. That's exactly the 3/2, 3/2 total angular momentum state. So one-to-one correspondence, that's nice. Okay, now we move down to the next one. And so the 1, -1/2 state, that has a matrix element of square root of 1/3. And this last one is just 1 here. So everything else in these 2 rows is 0. Everything else in the last row is 0. So these are all the matrix elements between the direct product state on the left and the total angular momentum state along the top. This is the matrix elements you need. And so now we can write out this expansion. Right? These are the matrix elements we needed to write out this expansion that we wrote down here. So this is the expansion we need to go from one basis to the other. And this is the table we just wrote down of these constants that we need. So let's start going through them. And we'll start with the easy one. So y10 up is our 10 half in this direct product notation. And this is our M1 and this is our M2. And here's, this column is our M1, this column is our M2. So this state here, our 0, 1/2 state, this 1, 0, 0, 1/2 state is this guy right here. Right, here's our 0, 1/2 state. This state was also our PZ. Y10 was exactly PZ. Right, PX and PY are linear combinations of Y11 and Y1-1, so we'll worry about it. Let's just start with this one where there's a direct one-to-one correspondence. The PZ orbital we're working with, Y10 and this. And so now I go up to the table and I can immediately write down that PZ up is equal to, well, I look at this column here and I just go across that row and I see what the coefficients are. So it's the square root of 2/3, and then I go up to the I just go up to the top of the row and read off what that state is, times the 3/2 1/2 state, and the next coefficient is minus root 1/3, and I go up to the top of that column times the 1/2 state. And that's the way you do it. So this is the total angular momentum state, J comma M, J comma M. All right, so we've written our mixed basis. This is so over on the left we have our mixed direct product basis. And on the right we have our pure angular momentum basis, which is what we need. So that's how you use this table to go back and forth. And once you have this table, it's very easy to start writing these down. So let's just write, we'll need the rest of them. So wish I could keep this table in front of us. Let me see if I can copy it. And so now let's see what we can do. So we can do Y10 down, which is our PZ down, which in this notation we're using is our 10 1/2 minus 1/2 state. So again, this is our M1 is 0 and our M2 is -1/2. And so I go up to my table. Here's the 0, -1/2 state over here. So I just go across that row until I find some non-zero matrix elements. And so I can immediately write down that PZ down is equal to root 2/3 times, when I go up to the top of that column, so that's 3/2 minus a half plus root 1/3. Go up to the top of that column, and that's 1/2 minus a half. So that's, we've taken care of our two PZ orbitals and written them in terms of our pure angular momentum basis. And in this basis, that operator L squared minus or J squared minus L squared minus S squared is diagonal. So in this basis, we know how to take the matrix element of this HSO. Now we just need to do the other y11 and y1 negative 1, and then make the linear combination of them. y11 up is, in our new notation, y11 1/2 1/2. Right, again, this is, the first one is M1 and M2. And so I go up here and I look for the 1/1/2. Oh, that's this guy, 1/1/2. Oh, that's easy. There's only one matrix element. It's 1, so that's exactly equal to the 3/2 3/2 state. How about another one? Y11 down. So in this notation, that's 1 1 1/2 negative a half. So I look for M1 and 1 negative a half up here. 1 negative a half. That has two matrix elements, so that's equal to root 1/3. Go up to the top of the column, 3/2 a half plus root 2/3. Go up to the top of the column, that's a 1/2. That's y11 down. And now we just need y1 negative 1. Okay, so y1 negative, where are we? y1 negative 1. y1 negative 1 up spin. So I look for negative 1/2, which is this guy here. Negative 1/2. I go over, look for the non-zero matrix element, so that's square root of 1/3. Go up to the top of the column, it's 3/2 negative a half. And minus root 2/3. Go up to the top of the column, it's a half minus a half. And one more we need is y1 negative 1 down, which is 1 negative 1 half negative a half. So that's this final guy down here. Negative 1 negative a half. There's only one matrix element, it's 1, so that's exactly equal to the 3/2 negative 3/2 total angular momentum state. So those are all the transformations from the y's to our total angular momentum. Of course, we don't work in the y basis, we work in px, py, and pz. So there's just one last thing we have to do. We already know the pz. We did the pz, we need px and py, because they're linear combinations. So the final thing we need is to get the px and py states. So px up is 1 over root 2 y1 negative 1 up minus y11 up. Right, the px and py were linear combinations of the y's. And we have the y's in terms of our total angular momentum, so we just add up what we've already done. So px up is equal to 1 over root 2 times square root of a third, 3/2, negative a half, minus square root of 2/3 times half, negative a half, minus 3/2, 3/2. All I did was I added up what we had written down for y1, -1, up, and y11, up, and added them. Well, actually subtracted one from the other. That's px up. I mean, there's no real, easy way of doing this. It's just a lot of detailed steps. So that, again, px up is just, well, px is a linear combination of y1, -1, and y11. We just switched up spin to down spin. And so then if you write down what we just wrote, write your y's and y up and y1, -1 down, and y11 down in terms of the total angular momentum, which we just did, we get the px down. And the last one is the py's. So that's our complete change of basis from our px, py, pz basis that we've been using to this total angular momentum basis. And in this total angular momentum basis, we're now able to take the matrix elements of the spin, orbit, Hamiltonian. Let's see what that looks like. So now that you have this, we can evaluate the spin, orbit, Hamiltonian matrix elements. I guess I kind of forgot to mention in the very beginning when we wrote down our spin, orbit, Hamiltonian, this guy. This guy is what you call local, which means it only acts, it has matrix elements between states on the same atom. So you only get matrix elements between states on the same atom. So it's only going to couple like A to A, just ignoring everything else, or B to B, at least in this approximation, the way it's used. And if you think about the way we drew that picture, you've got the state circulating, the electrons circulating around on this atom, creating this magnetic field that interacts with the spin of the electrons on this atom. So it doesn't affect in any way the off-diagonal matrix elements. So it doesn't change, like what were we using, VXX or VSS, the off-diagonal matrix elements that couple one atom to another. And I guess that kind of brings us to the end, so we'll actually evaluate the matrix elements next time and show what happens to the valence band. We'll meet Friday at 3:10 as usual, I guess, in my lab again, because it's easy, and to discuss the graphene homework.